In the next two videos, we're going to be talking about the Cope elimination and the Hofmann elimination. Now, both of these reactions involve amines. They involve RNH2 functional groups that ultimately get converted to alkenes. They get converted to CC double bonds. Now, that being said, both of these reactions also have key differences that you should be aware of. So in the first video, we're going to be talking about the main aspects of the Cope elimination, and in the video after this one, we're going to be talking about the main aspects of the Hofmann elimination so that you know about the key differences between these two types of reactions. So let's start with the Cope elimination. Now, the first key characteristic about this reaction is that it is a concerted reaction, which means that all bond cleaving and all bond formation takes place in a single step. So as a result, when you break a bond, when you form a bond, all of that takes place only in one step for a concerted reaction. And the Cope elimination is an example of a concerted reaction. Now, for the Cope elimination, this reaction also involves syn-beta elimination. Now, we're going to get to the beta part later with our examples, but before I define what syn elimination means, I just wanted to let you know that if you have a problem involving Cope elimination, and it does not involve stereochemistry, there are no black wedges, there are no dashed lines defined, then you only should worry about beta elimination. However, if you do have stereochemistry defined, if you have black wedges present, if you have dashed lines present in your starting material, then you have to worry about both syn and beta in your elimination mechanism. Okay, you have to worry about both of these parts. When there's no stereochemistry defined, only worry about beta. When you do have stereochemistry defined, you have to worry about syn and beta. So we're going to get to beta soon with our examples. So what is syn? Well, basically an elimination reaction, when you have two groups or two atoms that leave a molecule, then what's going to happen is a double bond is formed on that molecule. However, for a syn elimination, the two groups, the two atoms that leave the molecule, they both have to have the same stereochemistry, which means that both of them have to be sticking out of the page, or both of them have to be sticking into the page, or both of them have to be on the plane of the page. So in a future example, we're going to see that this is actually the most convenient. It's most convenient for both of the groups or the atoms that leave the molecule for them to be on the plane of the page, because even though it might seem that both of them are sticking out or both of them are sticking in, if one is pointing up, one is pointing down, the rotation and the orientation, the overall format, it can be very subjective because these molecules are three-dimensional and you have to take into account a lot of small details in terms of their conformation and their rotation relative to one another. However, if both groups or if both atoms that leave the molecule, if they're both on the plane of the page, it kind of eliminates confusion. So we want this for our Cope elimination reaction, at least in the example involving stereochemistry that I'm going to be giving you in this video. And finally, for the Cope elimination reaction, you have to eliminate the more substituted beta hydrogen atom. Okay, so I forgot to write the beta, but it is supposed to be a beta hydrogen atom that you are eliminating, which is why we have the beta elimination here. So this implies that one of the two groups that leaves the molecule for a Cope elimination is going to be a hydrogen atom. So what's the second group? We're going to get to that right now with our first example. So this is our starting material, this is our product, and the Cope elimination is divided into three steps. So in the first step, you add two equivalents of methyl iodide, MEI, as well as K2CO3 to help with the addition of MEI. In the second step, you add hydrogen peroxide, H2O2. In the third step, you add heat and you form your product over here. So now let's divide these three steps into their respective components. So here we have our starting material again, and when you add two equivalents of MEI and K2CO3, all that happens is that the H atoms in your original NH2, these H atoms are replaced with your Me groups because you add two equivalents of MEI, therefore you have two methyl groups that replace the two hydrogens in NH2, and therefore you end up with an Me2. The rest of the molecule is the exact same. Now, once that's finished, then we add hydrogen peroxide. So what happens? Well, first let's examine this molecule over here. Here's a nitrogen atom. It's bonded to, it has 3 bonds, right? It has 3 covalent bonds and it has a lone pair. Once you add the H2O2, now the nitrogen atom, it's going to have 4 bonds and it's going to have a plus charge. And the 4th bond, the new bond it's going to have, it's going to be a covalent bond to an oxygen atom, and this oxygen atom is going to have a negative charge. So this is where the beta elimination part comes in. And it's also when rule number 3 also comes in handy. So now what's going to happen is one of the lone pairs on the negatively charged oxygen atom, it's going to grab a beta hydrogen atom. When it grabs the beta hydrogen atom, the hydrogen atom leaves the molecule, and the NMe2O group, it also leaves the molecule. And as a result, we have a double bond that forms. However, let's define what a beta hydrogen is in the first place. So here we have our NMe2O group. The carbon atom that is directly attached to it, it's called the alpha carbon. And all of the carbon atoms that are directly attached, or in other words, all of the carbons that are right next to the alpha carbon, we're going to call them the beta carbon. So this is a beta carbon, this is a beta carbon, and this is also a beta carbon. Okay? Now, all of the hydrogen atoms that are bonded to a beta carbon, they are known as beta hydrogen atoms. So remember, we have to eliminate the most substituted beta hydrogen atom. So which hydrogen atom do we substitute? Before we get to that, I just wanted to let you know that these 2 beta hydrogen atoms are equivalent, these 2 beta hydrogen atoms are equivalent, and these 3 beta hydrogen atoms are equivalent. So first we have to identify the beta carbon of interest. Which beta carbon? This one, or this one? Before we get to that, I also wanted to let you know that there is no difference between this beta carbon and this beta carbon. It doesn't matter which one you attack because the molecule in this case, it's symmetric. So therefore, you can attack either this one, this is your option 1, and your option 2 is attacking a hydrogen atom on this beta carbon. So which one do you choose? Do you choose option 1 or option 2? Well, let's go with this one first. So this hydrogen atom, it's bonded to this beta carbon over here, right? This carbon atom is bonded to 2 other carbons. Now, this carbon atom is equivalent to this one because this carbon atom is also bonded to 2 carbon atoms, and it's the same distance from this ethyl group, same distance from this group, same distance from this group. There's symmetry involved. So therefore these 2 beta carbons and therefore these 2 beta hydrogens, they are all equivalent. Now let's go to this beta carbon. So this beta carbon, it's only bonded to 1 other carbon. So therefore this beta carbon is less substituted because it's only bonded to 1 other carbon, this one. However, these beta carbons, they are more substituted because they are bonded to 2 other carbons. This one is bonded to 2 other carbons, and this carbon is also bonded to 2 other carbons. And it doesn't matter which beta carbon we choose. You can choose this one or this one because, once again, it doesn't matter because we have a symmetric molecule in this case. Symmetry is retained. It is maintained. It is still present. It is not broken. So therefore, let's just pick this beta carbon, okay? So what's going to happen is the lone pair is going to attack this beta hydrogen, and remember the beta hydrogen is attached to the beta carbon over here. Okay, so it's going to attack this hydrogen atom, and this bond over here is going to get pushed over here. So that's going to be the double bond formation. It's going to be the alkene formation. Now remember that carbon should have 4 bonds. So what do? We have to break this bond off so that it can form a lone pair on the nitrogen atom, and therefore in your final product, all of the carbons should have 4 bonds, okay? We have this double bond here because we pushed this bond over here. Now, when this oxygen atom, which is negatively charged here, when it grabs the H, it's going to become an OH, and when you push these electrons to the nitrogen atom, we're just going to have the lone pair again on nitrogen, and the nitrogen atom is still bonded to O, and it's still bonded to the 2 methyl groups, so everything is as it should be, okay? That is our first example. Now let's go to our second example, which involves stereochemistry. So again, since we're focusing now on stereochemistry, therefore the syn part of syn beta elimination, we have to follow that. We still have to follow the concerted step, and we still have to eliminate the most substituted beta hydrogen atom. Oh, also, in terms of the concerted step, this over here is the concerted step because this is where all of the bond breaking and all of the bond formation occurs. So we have a bond formation elimination, bond breaking, and this is also, you can consider this a bond breaking because this bond breaks, but then we also have a CC double bond that forms, and over here this bond breaks to form a lone pair. So therefore all of the bond breaking, all of the bond formation occurs in one single step, this step. So therefore this is the concerted part of the Cope elimination reaction. So now let's go to our second example, which once again involves stereochemistry. We have a bromine group sticking out of the page, and we have our NH2 group sticking into the page. So when you add two equivalents of MEI as well as K2CO3, again, what's going to happen based on what we discussed in our first example, the H atoms are just going to be replaced with the Me groups. They're going to be replaced with two methyl groups. So we just have this. When you add H2O2, hydrogen peroxide, now nitrogen is going to have 4 bonds. So then once we have this, we add heat and we form our final product. So remember, we have stereochemistry now, which means we have to worry about the syn part of syn beta elimination, which can make it a little bit more confusing because when I was actually taught this, the professor talked about rotating it 60 degrees, rotating the other side 120 degrees, clockwise rotation, counterclockwise rotation, and online it talks about Newman projections. It can be very confusing, and also molecular model kits. It's just not too clear, in my opinion, to get taught this part in that method. So what I've devised is a hopefully simpler method to help you guys solve these types of problems. And what I do is, instead of talking about degrees or like rotations per se, I try to get to this product in terms of swaps. So the way it works is this. So first of all, we have to identify the beta hydrogen we want to eliminate. So remember, this is the alpha carbon over here, which is bonded to the NMe2O group. So, and the carbon atoms that are next to the alpha carbon, they are the beta carbon. So this is a beta carbon, and this is a beta carbon. Now this is a beta hydrogen atom because it is a hydrogen atom that's bonded to a beta carbon, and there are also beta hydrogen atoms over here. However, we're going to focus on this beta hydrogen atom because this beta carbon is more substituted because it's bonded to 2 carbons, and it's also bonded to a bromine atom. This beta carbon is bonded to 2 carbons, and that's it. So therefore, this beta carbon is more substituted, which means that its beta hydrogen is also more substituted, which means that this is the beta hydrogen that we are going to eliminate. So now we have to talk about the swapping. So how does the swapping work? For the side of the molecule that involves the beta hydrogen, you have to swap twice, okay? And for the side of the molecule that involves the NMe2O group, you only have to swap once. So by swapping, I mean this. What we want to have happen is we want the beta hydrogen to be on the plane of the page, and we want the ONMe2 group to be on the plane of the page to avoid any confusion about syn, okay? Sure, it might seem like they're both sticking into the page, but then this is oriented up, this is oriented down. You have to talk about conformation and rotational degrees and all this stuff. It can be quite confusing. So to avoid all that confusion, we just want both of them to be on the plane of the page to make it simpler for all of us. So for this side, okay, we're going to focus on this side first. So we want to move this to the plane of the page. This methyl group is currently on the plane of the page. So therefore, we just swap these two. We just swap the H atom and we swap the methyl group. We swap their positions. When you do this first swap, you're going to end up with this. Now the hydrogen atom is on the plane of the page and the methyl group is pointing into the page. However, we're not done because we've only done one swap. So for the second swap, we're going to deal with the bromine atom and this methyl group. We leave the H group alone because it's already on the plane of the page. So we do the second swap, we just switch these two, and what's going to happen is now the bromine atom is pointing into the page and the methyl group is pointing out of the page. Therefore, we have our two swaps, okay? Now for this side, we only swap once. So we want this ONMe2 group to be on the plane of the page. So how do we do that? Well, guess what? This ethyl group is on the plane of the page. So we just switch the ethyl group and we switch the ONMe2 group. We just swap them. We just switch them once. And we leave this hydrogen atom alone. Leave it alone, okay? And by the way, this hydrogen atom, it's not a beta hydrogen. It is actually an alpha hydrogen because it is attached to the alpha carbon, okay? Just wanted to let you know. So we swap these two groups, the ethyl and the ONMe2 group. And what happens is now this ONMe2 group is on the plane of the page and the ethyl group is sticking into the page, okay? And remember that our H atom is also on the plane of the page, the methyl group is sticking out of the page, and the bromine atom is sticking into the page, okay? So now one of the lone pairs on the negatively charged oxygen atom can attack the hydrogen. This bond gets pushed over here to form the double bond, and then this bond gets pushed over here to form the lone pair on the nitrogen atom. And therefore, when all that is said and done, we have this final product plus NMe2OH. That's pretty much what happens. And how did I have this orientation over here? Well, now the bromine atom is pointing down. This ethyl group is pointing down. Both of them are sticking into the plane of the page, so now we know that they're on the same side, okay, of the double bond. This methyl group and this H atom, they're also pointing down, and they are also sticking out of the page, so therefore we know they're going to be on the same side. So the reason why we didn't think of these two as syn is because we didn't have a straight line over here. We didn't have a straight line. We had this bent line. So there was bending, there were rotational degrees, there was conformation to worry about. Once you have it straightened out like this, in the unstable transition state, now we know that these two are actually syn, and these two are actually syn, and these two groups are actually syn, okay? That's how I drew the final product over there. And again, this is the concerted part of the reaction because all bond breaking and all bond formation occurs in a single step.